in this particular lecture, we are going to continue with the discussion of Laplace's equation in spherical polar coordinates. And today we are going to do a few problems and a few things that are indeed maybe asked in the examination as well. And these are quite important topics as well. So we were already discussing, I think, Laplace's equation in spherical polar coordinates. And so here it is. So what I will do is, okay, just give me a minute. So we have arrived at the solutions of the Laplace's equation. We have arrived at the solution for the Laplace's equation in spherical polar coordinates. And today we are going to move further from there only. Just let me share the screen. Okay. So we've already derived that when there is an azimuthal symmetry, we already know that when there is an azimuthal symmetry, that is, there is as such no phi dependence. There is as such no phi dependence. Then the potential V in general is given by, like in spherical polar coordinates, I'm saying about spherical polar coordinates. Spherical polar coordinates, if I'm saying, okay. And if I'm talking about spherical polar coordinates, and in V in general, if I'm talking, and if there is no phi dependence, of the solution for the Laplace's equation, that is del square V, yields you a solution which is like this. This is A r raised to power L plus BL. So this will be like AL. And this is like r raised to power L plus 1. And then there is PL cos theta. And these PL cos theta, you already know that these PL cos theta are Legendre polynomials. Okay. In general, one must note that as r tends to infinite, this particular term would blow up. And as r tends to 0, this particular term would blow up. So V inside potential in general is given by AL r raised to power L, and then you have this PL cos theta. Okay. And V outside r comma theta is given by BL upon r raised to power L plus 1. And then you have this PL cos theta. This is how you can write potential inside the sphere and potential outside the sphere. Now a question arises, what if V naught theta, that is potential, is specified on the surface. Potential is specified on the surface of the sphere. On the spherical surface, if it is specified, that is, if it is specified that the potential at the spherical surface is V naught theta, then how to find potential inside as well as outside? So this is one of the questions that one needs to investigate. So if V naught theta is specified on the surface, so let me write it all over here. So if V naught theta is specified on the surface, if V naught theta is specified on the surface, let's say the radius is capital R, then I can write, and assuming that there are no charges, that is assuming that there are no charges, we are asked to find potential outside. We want to find potential outside. Now, one must remember that potential in general across the boundary remains continuous. So potential remains continuous on the boundary. One must note that potential remains continuous on the boundary. And if like this is the case, then I can write that my V outside at r comma theta should be equals to V naught theta. By continuity, I can write that my potential outside as r tends to capital R, it should be equals to V naught theta. If this is the case, then then I should write BL upon R raised to power L plus 1 PL cos theta should be equals to what? Should be equals to V naught theta. Okay, this should be the case. Now understand what we are going to do. What we are going to do is we are going to use the orthonormality. No, we are going to use the orthogonality condition for Legendus polynomial in order to extract all these BLs. And once you find BL, you can find potential anywhere outside. Is that clear? I think this is quite easy to see that if I know my potential anywhere outside, if once I know BL, I can find potential anywhere outside as well. Okay, so what I'll do, I'll simply do one thing, and that particular thing would be to simply integrate both of the sides by PL dash cos theta sine theta d theta. I have to multiply both of the sides by PL dash cos theta sine theta d theta, and integrate from 0 to pi. Integrate from 0 to pi. Okay, because you know that orthogonality condition in Legendus polynomial is given by -1 to 1 PL dash dx is given by 2 upon 2l plus 1 Kronecker delta LL dash. So this is how it is given. Okay, now instead of x, if I write theta cos theta, then I can play with the limits. Like I can play with the limits from 0 to pi, and this dx would become sine theta uh, sine theta d theta. This is something that we've done in the previous lecture as well, while we were trying to extract the potential anywhere inside. Now we are doing potential anywhere outside. So if we want to find potential anywhere outside, so I will do the same exercise. I will try to do this. I will try to integrate from 0 to pi. This is like summation BL upon R raised to power L plus 1. Then I have this PL cos theta. I will multiply with PL dash cos theta, and then I will write sine theta d theta integral, and also write here V naught theta, and here I'll write PL dash cos theta sine theta d theta. Okay, from 0 to pi. And I've also made it clear that only non-zero solution would come out if L is equals to L dash, sorry. If L is not equal to L dash, then this particular integral would become 0. This particular integral would become 0. So what I will write, I will simply write it as 2 upon 2L plus 1, 2 upon 2L plus 1, Kronecker delta LL dash. This is how it is. And I know that if L equal to L dash only, then this will give me 1. Otherwise, it will give me 0. So the entire integral becomes 0 anyway. So I'll not write this 2 upon 2L plus 1. I'll write BL here, and I'll write R raised to power L plus 1 here, is equals to what? Is equals to integral 0 to pi. And this, you have V naught theta PL cos theta sin theta d theta, because L is equal to L dash. So I have written, instead of L dash, I have simply written L. Now, what will come out here? Here you can see BL would come out as 2L plus 1 upon 2, and then you can have R raised to power L plus 1, and then you have integration from 0 to pi, and then you have this V naught theta PL cos theta sin theta d theta. Okay, once you find BL, now you can find the potential anywhere outside the sphere. Now one can find potential anywhere outside the sphere. Okay, so this is how we can find the potential anywhere outside. We've done potential anywhere inside using the same formulation. Now I've proved the same thing for Q for potential anywhere outside the sphere. Now, in general, let's say an example I'm taking. Let's take an example. If potential on the surface of sphere is specified as pi naught cos square theta, then find the potential outside as a function of r and theta. We have to find this. I'm giving you a minute just to see this question, and then we'll do it all. Okay, so if the potential on the surface of the sphere is specified as phi naught cos square theta, and we have to find the potential outside anywhere as a function of r and theta. How to go about this problem? So now on the surface, I'm given the potential phi naught cos square theta. So I'll write it as phi naught cos square theta is nothing but it is equal to V r comma theta. Okay. Now I know that anywhere outside my potential in general is given by summation BL upon R raised to power L plus 1 PL cos theta. This is how my potential anywhere outside is given. So potential anywhere outside is given by this way. And I know that in the limit as R tends to capital R, my potential R comma theta would come out as phi naught cos square theta. Would come out as phi naught cos square theta. Okay. Now by doing this, we'll be able to find by doing this, what I can do, I can expand both of the ends. And I know that since here only quadratic term is here, so I will expand till quadratic terms. I will expand till quadratic terms. Okay. So I will expand till quadratic terms. What it will be, it will give me first term would come out as B naught. Then the second term will come out as B1, B2. And beyond B2, I'm not going to expand. Because see, why I'm not going to expand? Because if I expand till B3 also, B3 contains a cubic term and a linear term. Sorry, P3 contains a cubic term as well as a linear term. There is no linear term, there is no cubic term. So P3 would B3 would be 0. No doubt in B4 you will have a quadratic term. In P4, sorry, you will have a quadratic term. But point is this, that B4 would be 0 because there is no as such biquadratic term. So what I'm going to do, I'm going to expand it till B naught upon R. Then I'll write B1 upon R square. And then this will be like P1 is this. B2 upon R cube is simply 3 cos square theta minus 1 upon 2. And this is all equals to phi naught cos square theta. Now, if we compare both of the sides, we can understand that our B1 would be 0. Why B1 would be 0? B1 would be 0 because your cos theta term is not nowhere present, so it will be 0. Your constant terms, that is B0 upon R divided by B2, minus B2 upon 2 R cube, this will be equals to 0. And further, as you know that your B2 upon 2 R cube, and this is 3, this is cos square theta, will be equals to phi naught cos square theta. Okay, this will be equals to phi naught cos square theta. From here, you can extract your B2, and your B2 will come out as this cos square theta gets cancelled, 2 phi naught R cube upon 3. So 2 phi naught R cube upon 3 is your B2. So this is what I'm writing here. And what would be my B naught? My B naught would be 1 upon 2 R square. So if I use that to phi naught, like this is R square, because you see there is R cube here. So what I will do, okay. So this will be like phi naught R upon 3. If I'm not wrong, kindly see that. I think this will be phi naught R upon 3. Is that clear? I think it is clear. If I write phi naught r upon 3, this will be clear. Okay. So now B naught has been found, B2 has been found. In order to write potential outside anywhere, I will write potential outside anywhere as a function of r and theta as phi naught capital R upon 3. And since it is B naught, so there will be a small r here. And then plus, I will write 2 phi naught upon 3. And then you have this r cube. And then you can write P P2 cos, so P2 is 3 cos square theta minus 1 upon 2. And since this is P2, so this will be divided by R cube as well. So more appropriately, if you want to write, this will be like phi naught upon 3, capital R upon small r plus 2 phi naught upon 3. This will be like capital R upon small r raised by whole cube. And then you can write 3 cos square theta minus 1 upon 2. Is that clear? Next, we are going to move. So I think this discussion is clear. A similar thing we have done for potential inside in the previous discussion. Although understand this is the most general result, it may not be asked in the examination as such, but overall understand that this approach will be very fruitful for examination. So you just whenever you are given the boundary condition, whenever you give the potential anywhere on the surface and you are asked to find potential inside or outside, you just use the expression of potential inside and outside, place R equals to capital R, compare the terms, and then you will be able to find the corresponding AL and BL. And once you find corresponding AL and BL, then you will be able to find potential inside as well as outside. Now, next is an important problem. It is called as conducting sphere in a uniform electric field. In a uniform electric field. So conducting sphere in a uniform electric field, I'm going to do this particular problem for you. Okay. And in order to solve this particular problem, one needs to understand a few property of the conductors as well, a few properties of conductors as well. Okay, so let us consider that this is our conducting sphere. So this is our, I'll write uncharged conductor, and this is placed in external electric field. So external electric field, let us take it in the direction of Z. So this is in the Z direction. So I'm writing in the Z direction. And because of the charge distribution, slightly the field will get distorted, no doubt. Okay. You also know that you're on the conductor, electric lines of force enter normally and they emanate also normally. So they enter normally and they also come out normally to the surface. Okay, so that is one thing. So this is your electric field, and this electric field is along the Z direction, that is E naught K cap. This is your electric field. Now, one of the points that I need to make you understand here, that initially when we were doing the questions previously, we were writing V inside R comma theta as summation AL, some R raised to power L, some PL cos theta. And then anywhere outside, we used to write this in this fashion. Okay. Understand that this was true only if your potential is going towards zero as R tends to infinite. This particular thing was only true if your potential was going towards zero as R tends to infinite. Okay. But in this case, you can see that your electric field is given along K cap. So your potential can be written as minus del V upon del Z can be written as E naught. And you can find that your potential is minus E naught Z plus C. So this is one thing that you can see, that as Z tends to infinite, or more appropriately, I can write in spherical polar coordinates, your Z is equal to R cos theta. So your potential as a function of R and theta comes out to be in this fashion. Minus E naught R cos theta plus C. Okay, so minus E naught R cos theta plus C has come out. And you know that if I go towards infinity, that is R tends to infinity, my potential is going towards infinity. So no longer I can write in this way. I mean, I cannot bifurcate my solutions into two halves now. Okay, so I'll have to consider the general solution. Now let us first make our problem statement. The problem statement is that this uncharged metallic sphere, or you can say conductor, is placed in a uniform electric field, is placed in a uniform electric field that also along z-axis, okay, that also along z-axis, given by E naught A cap, okay. What will happen? One thing that is for sure is that your uh, there will be induction of charges because there's an electric field, so your positive charge will get induced on the inner side of the northern hemisphere, and on the southern hemisphere you will have a negative charge induced. You will have induced negative charges on the southern hemisphere. So I'll write it here. So as a result, there will be positive charges induced, positive charges induced on the northern hemisphere and negative charges on the southern hemisphere. And negative charges on the southern hemisphere. Okay, so this will be the result. So what will happen? Okay, also understand because of this induced distribution of charges, there will be some distortion of the field as well, which I have shown here. Like, there would be some distortion of field because now there is no longer electric field. So closer to this, there would be some induced electric field as well. So a distortion can be expected near the conducting surface. Now, what do we want to find? We want to find potential in general anywhere outside the sphere. See, we want to find in the region outside the sphere. Okay, so how to go about it? So in order to think about this particular problem, let us first understand a few properties of conducting surfaces. So one property of conducting surface is that our conducting surface is an equipotential. First thing is that our conducting surface is an equipotential. So you should understand that our conducting surface is an equipotential surface. By equipotential surface, one needs to understand that this has potential it has a constant potential. And if it is a constant potential, uh, we can take this constant potential as zero. We can take this constant potential as zero. Okay, this is like why we have taken it zero, because you should understand that potential in general is a reference dependent term. And if I know that my potential is constant over conducting surface, why not take it as zero? So I've taken the potential as zero, and also understand because of the induction of the charges, if this is placed in external electric field, due to the induction of the charges, this will be the case. Okay, and if you just visualize your xy plane, if you just visualize your xy plane, which is z equal to 0, this will be at zero potential, because see, the distance of these charges from on the northern and on the southern, like this particular plane, if you take the distance, like these charges, if you take from the like distance from the equatorial plane, if you try to take these distances, and these distances are equal, like this particular plane is equidistant from like whatever distance is here, like radially, if you see that these are all at these all positive charges induced are at radially r distance from the center. Similarly, you have these negative charges. So by symmetry, you can expect that your potential would be zero on the equatorial plane. You can take like q upon r, then there is similar minus kq upon r here. So overall, the potential, net potential on this equatorial plane by symmetry, you can take it as zero. And you understand in general, your potential is minus E naught Z plus C. So you know that your potential E naught, it is E naught Z plus C. At Z equal to 0, your potential is 0. That implies your C would be 0. Okay. So in general, your potential gets reduced to minus E naught R cos theta only. Now there are two boundary conditions. One of the boundary conditions I have already specified. One of the boundary condition is that the equipotential surface has the potential 0. On the equipotential surface, we have potential as 0. Okay, so on equipotential surface, we have potential 0. So what I'll do, at r equals to capital R, our potential is 0. Okay, and then another condition is, that as r tends to infinity, now potential would survive, and that survival is given by minus E naught r cos theta. So now no longer I can say that my potential is is getting 0 at infinity. Now you can see that your potential is still there, potential is still there, that is minus E naught r cos theta. Okay. So using the first condition, this will be my first condition, this is my second condition. So as r equals to r, your b r comma theta would be 0. That implies your al r raised to power l plus 1 plus bl upon r raised to power l plus would be equal to 0. That implies your bl can be written as minus al r raised to power 2l plus 1. Okay, so r raised to power 2l plus 1. This is how you're going to write. Now, potential anywhere, because no longer you can say that my potential outside is given by bl upon r की power l plus 1 pl cos theta. Now I have to write my potential as this. And I know that this potential as r tends to infinite also remains to be minus E naught r cos theta only. So in any way, it will remain this way. So as r tends to infinite, this will go to 0, and you are having this term. What would if I have to as r tends to infinite, this term would go 0. So I will have to expand this particular term, and I will get what? I'll get A naught plus A1r cos theta is equals to minus E naught r cos theta. So from here you can clearly see that your A naught is 0, and from here you can clearly see that your A1 is equal to minus E naught. Once you know your A1, you can also write your B1. So your B1 would be equals to what? Your B1 would be equals to minus A1 into R cube. Your B1 would be minus A1 R cube upon, minus, I'm so sorry, this will be like plus E naught, because A1 is minus E naught, no? So this will be E naught R cube. So overall your potential now outside in general can be written as A1 is A1 is minus E naught, and then you can write R cos theta, and then plus you have this term given by E naught capital R cube divided by R, and then this is, I think, cos theta. Okay, so now your potential is given by minus E naught R cos theta plus E naught R cube upon small r cos theta. And one must understand that this particular potential term is because of the induced charge distribution. This particular term, because see, this term was already there. This term was already there due to the presence of a net external field along the z direction. So this particular term is this modification which has been brought about by the induced distribution of charges. So this modified term, so your potential has been modified by the term given by E naught capital R cube divided by small r cos theta, and this term is due to the induced distribution of charges. This term is because of the induced charge distribution within the sphere. Okay, I hope it is clear. Now, if you want to find what is the induced distribution, what you can do, I have already, one understands that near the conducting surface, the normal component of electric field is given by the charge distribution as distributed, that is sigma upon epsilon. So what is the normal component to the sphere? The normal component would be the radial component. Normal component would be the radial component. And the first thing that one needs to investigate is what would be the electric field. So what would be the electric field? One can clearly see that electric field can be written as electric field can be written as minus grad of V. And if I write minus grad of V, I think this term would give you the result in this form that I want you to derive on your own. E naught plus 2 capital R cube divided by small r cube cos theta, and then you have this minus theta cap, and you have this E naught, and you have 1 minus capital R cube divided by small r cube, and then you have this sine theta. So, I mean, you can find this electric field that is minus of grad of V, and this will be it. Now, the normal component of electric field is nothing but the radial component. So, your radial component is the normal component of the electric field. So, I'll write the normal component of electric field is nothing but the radial field, and this is the radial field. Like this is the radial field, and that particularly in the direction at the point r equals to capital R. So at r equal to capital R, if you want to find the electric field will be equals to E naught, and this will be 3 because this is 2, and then this will be cos theta. What will be sigma then? Sigma would be epsilon naught into normal component. So this is 3 epsilon naught E naught cos theta. And this was clearly understood. This you can clearly understand that on the northern hemisphere, where your theta was varying from 0 to pi by 2, you had a positive charge density, which is very much clear because you can see that on the northern hemisphere, because of the electric field, you can see that positive charges will be pushed on the northern hemisphere, where like, and when theta is greater than pi by 2 and less than pi, that is in the southern hemisphere, since cos theta is negative for theta lying between pi by 2 to pi, you can have a negative charge density here. So this was very much clear. This expression I want you to remember, because this is certainly asked in the examination directly. As we go along, we'll also see that we'll also see the same problem in cylindrical polar coordinates, and all these kind of things, all these kind of problems are very important when it comes to examination. I hope I'm able to explain all these things to you, and I hope that you just pay attention to all these problems. If you find any problem in these in following these lectures, kindly let me know.